All right, good morning and happy Friday. I'm planning on doing the LeetCode Daily Challenge for today. So let me share my screen. So it's June 9th, and I'm getting a little bit later of a start today. It's 8:55 in the AM. Okay, so here we go. It is the 9th, and we're looking for the smallest letter greater than the target. Okay, so we should be able to do a binary search, I think. Have I solved this before? Wow, a long time ago when I first started LeetCode, around 6 years ago. Okay. Well, let's do this in all the languages that I've been coding in. I'll start with Python first. Here's an array of characters, and there's our target T. So we should be able to, we could just do a linear scan, right? A linear scan, and then we could also, just linear scan seems okay. The input arrays, A of characters. Started at 8:55 a.m. That's the game plan. Oops. Game plan. Okay, so let's start implementing it then. All right, so for each character X, the array of characters, or just say it's C then. If the ordinal value of C compared to this to be greater than, right? Let's see, so best difference will say best character has to be greater than that. Okay, so best, we'll just say it's equal to A initially. There are at least two different characters. Oh, it is sorted in non-decreasing order, right? So we should be able to do binary search eventually, right? So this is a O of N game plan, and then a logarithmic game plan will take into account the non-decreasing order of the input array A. So we want to return the first one that's greater than that, right? Return C. Guess, yeah, so just do a linear scan. And then here we can return just like the normal character. C, F, and X should be the output expected. Oh, come on. C, F, and C. Ah, okay. A sub 0 in case, okay, so that's the corner case. Okay, and that looks good, right? Let's do a linear scan. Okay, that works. So that's accepted. 8:58. Oops. 8:58 in the AM. So that took about 3 minutes for the implementation in Python 3, oops, which is accepted. Hey. Okay, that's a linear solution. So let's do a logarithmic solution. Yeah, we can just do a binary search, right? I don't know if we can bisect this or not. Let's try. I equals bisect right A for the target, return A sub I. Oh, if I is, yeah. if I is less than the length of A, otherwise return A sub 0. Okay, so that's logarithmic. Okay, cool. So let's see what we came up with 6 years ago. This must have been one of the first ones. Okay, yeah, it's one of the first ones I've solved. And let's just do this. A few solutions. And let's see. Yeah, and perform binary search for O of log in runtime. Kotlin, JavaScript, Python 3, Rust, C++. E. Mhm. Bound. Okie dokie. Something like that. Looks good. All right, that's cool. Right, Rust will find a partition point. JavaScript. Is there a O dash last index of? So let's just do this modulus a dot length. Something like that, right? So if it is in, then it'll just be back to 0. Really? Oh, no way. Index of. I thought that would have worked. Okay, let's just do this then, the old-fashioned way. O dash at last index of AT, turn I is less than a dot length, a sub I, otherwise a sub 0. Defined, undefined still, really? AT and I, oops. AT and I. Come on. Sorted last index, right? Sorted last index of. Really? What is this? Sorted last index. Well, what is of? I search on a sorted array. sorted last index, I guess, right? Okay, and that looks good. So let's do this sorted last, oops, last index. Right, so one liner should be okay. So if it is in, then it'll default to 0 if we mod it by n. Right, okay. Okay, that's cool. Let's do the same for Python 3. As we'll just change this guy into a one-liner. Lambda self AT, and just return a sub this guy modulus length of A. Looks good. Okay, that's cool. And then let's change this in C++ as well. Turn. A sub distance from A dot begin until here. Modulus size. Okay. Looks good. All right, that's cool. Okay, Kotlin and then Rust, and we will call it a day. Array of characters, target character, and if it doesn't exist, then it'll be the inverted version. Okay, so if var I equals a dot binary search for t, if I is less than 0, it doesn't exist. I equals negative I plus 1, and then we'll return a sub I modulus a dot size. Uh-oh. Oh yeah, binary search super T or target T. Let's see, come in upper bound. Binary search, right? Java's equivalent. Binary search. I'm using binary search, but binary search is not what I want here. Right, okay, we can just do this the hard way. Right, so Rij is a pair of 0 and a dot size minus 1, while I is less than j, and then we'll return a sub I modulus a dot size. K equals I plus j divided by 2 if a sub I dot 2 int less than a or a sub k. Wait a sec, hold on. What do I want to compare to what? Yeah, I want to a sub k. It's less than our target at 2 inch, right? And we can increment I to k plus 1. Otherwise, if it's too big, j equals k. Big money, no whammies, ho. That's not right. Well, if it's equal, we also want to +1, right? We want to go past it. CF, and okay, Y is not right. Why am I getting Y? Z, J equals K. It's not equal to it, K +1. If it's strictly greater than, so if it's less than or equal to it, then we need to make it bigger. It's greater than it. Oops. Oops, $I, J. Let's see what we got going on here. Maybe I should use the J instead of the I. I don't know. Let's see, 0, 0 for A, right? That's right. C is 1, 1. That looks right. 3, 0, 1, 2, 3. Y is not right. Z is greater than that, so. J needs to be size, not size -1 initially, and then I should be bumped up. Okay, that looks right. Big money, no whammies. Yay. Okay, there's Kotlin the hard way. That is given the sorted input array A. And target T. Return the upper bound of target T. If it exists. If it exists. Otherwise, a return A sub 0. Modding. Modding, right? By modding the length index by the cardinality of the input array A. All right, whatever. I mean, it's pretty straightforward, right? Okay, and then we'll do Rust. We use the partition point within Rust. Oops, Rust. Okay. And I equal A dot partition point T. Actually, we'll return A sub that modulus A dot length. I think that works, right? No, found char. FN mute closure. What? Hold on. Okay, rest partition point. Come on. Partition point. Oh, I see. Okay, partition point. Okay. Each character exceeds a target T, right? CC, oh, that's not right. Partition point, predicate, first element of the second partition. So the first partition is this guy, and the second partition's after that guy, right? I think that looks right. No, what the heck? Okay, so some reason the partition point character is less than or equal, or is greater than or equal to the target. Character is less than or equal to the target for the first partition, and then it'll be strictly greater than the target for the second partition, right? Okay. Okay, a little bit confused, but not too bad. Yay. Okay. There we go. Actually, might as well just stick this on one line so it doesn't take up terribly too much more white space. And it's pretty straightforward, right? Okay. Yay. Here we go. Perform binary search for O of log n runtime that is given the sorted input array A, find and return the upper bound of target T if it exists. Otherwise, return A sub 0 by modding the ith index by the cardinality input array A. Yeah. Let's see. There we go. Right, perform binary search for O log n runtime and is given the sorted input array, find and return the upper bound of I guess return the A sub ith bound. Yep, that sounds good. Okay, let's see what other folks came up with solutions real quick, and then okay, doing the binary search manually. And manual binary search. Python no brainer. Okay. Yeah, bisecting is fine, right? Upper bound, same thing. Okay, cool. Some of these solutions are decent. I still have a biased opinion. I think mine's the coolest. I mean, modding by n is cool, I think. You know, it's like a neat way to get back to A sub 0, like modding by the cardinality input array, right? Rather than having more code to check that explicitly, right? So my solution, and I have a biased opinion probably about my own solution, right? But I mean, this is awesome. I think this is so cool, right? So use the Lodash. Here we're using the built-in functions, right? If it's a built-in function, you might as well use it, right? And then it's good to know what's going on under the hood as well, right? So logarithmic amount of guesses, and then you divide and conquer to the left and right. So we have the search space each time we iterate through the binary search for a logarithmic solution. Okay, so yeah, that's all she wrote, right? Pretty awesome. All right, catch you all later.